All right, now we are going to work our way into the group SU2, right? So in our world, what is this? These are the group of 2 by 2 unitary matrices with determinant equal to 1, and they are complex matrices, right? We usually, since unitary gives us complex, that's a bit redundant, so usually you'll see it written just as SU2. Now we're going to get there, though, going through U2, which is just the unitary matrices, the unitary 2 by 2 matrices. And so you'll remember the way this worked, right? Is we were able to define this thing. This is the set of all matrices U. Let me write down the actual expression. IR conjugate times GRS USJ, which we went through all of this before, but the total notational stuff means U Hermitian conjugate G, that's a lousy G U. This guy has to equal GIJ, and furthermore, GRS is delta RS, right? And this has to equal, it has to preserve the metric, right? But it's preserving a specific metric. It's preserving the metric with ones all down the diagonal, right? So the beauty of this is we just have to write U Hermitian conjugate U equals I, and that's because we're choosing this particular metric. And we went through in the earlier lectures how to interpret this as a metric without running into any of the pitfalls I warned about in the What is a Tensor series, understanding that that interpretation is what ultimately leads to this transpose and the sesquilinearity of the fact that it's a complex matrix. We have the transpose there. And so this is sort of the rule that defines this group. And we talked about that in our long section on classical groups. So we want to kind of discuss this. And what we're going to do is we don't know the exact form of this group, but we're going to actually figure out what the Lie algebra is using some basic definition work. And then we're going to discover the form of this group, meaning the form of this group, when I say that, what I mean is we're going to discover how each of these matrices, right, these are 2 by 2 matrices, so there's 4 elements. If I take the 1, 1 element, I'll be able to say the 1, 1 element is a function of several parameters. And the number of parameters is going to be the eta. We don't even know what the eta is for U2, right? But we're going to kind of figure that out. So we're going to be developing, we'll start with some Lie algebra, which I guess we'll call U2 with a script U. And that Lie algebra will exponentiate into the full group. So we're going to figure out what this is, and then we're going to exponentiate it, and then we're going to be able to calculate every matrix in the group. Okay. So again, we're kind of emphasizing the algebra as our starting point in this case. Okay, so let's do it. All right, so what do we know? We know this formula. Now notice that U is just a member of this group. We're not saying that the determinant of U equals 1. If we were, then this would be SU2. But we're just using U, so all we know is this expression here. All right, so we go to this group and we say, all right, let's look right around the identity. Right around the identity, those are going to be matrices that we should be able to write down as I plus something that's a very sort of small matrix, right? So we got to figure out what that is, but we know what that comes from. It comes from the Lie algebra. Now, we know that the Lie algebra is defined through derivatives of these guys, so we know that it's got to be, since this is a 2 by 2 matrix, right? I should make that really clear. This is the matrix 1, 0, 0, 1, right? Even though it's a member of the complex, these are supposed to be complex entries, but a real number counts as a complex number. It's a subfield of the complex number, so these are fine. But this, obviously, this unit matrix lives in here. That is this point, this green point, right? That point is represented by this matrix. So now we need some infinitesimal. Well, let's see. What do I want from my epsilon times some other matrix, right? And that will be an element of U2 in the neighborhood of the identity. So we have a few different ways of choosing how to do this, right? We could do it the way I just did it, where the matrix M has finite entries, but epsilon is really, really small, and it always drives the matrix down to being small. That's not a good way to do it. Where we could just say M and demand that the entries of M, whatever they are, be infinitesimal entries. All be very small size amounts in each matrix element. So that's a good way of doing it. And we could also put an I out in front and talk about the matrix M multiplied by I. That distinction, whether we write that or whether we go just M, is one of the sort of the distinctions between physicists and mathematicians' study of this. Gilmore actually does it this way, but understanding that M is a matrix with complex entries, putting an I out in front is an arbitrary move, right? It's an arbitrary step. It doesn't really change everything because you could just change the matrix M to some other matrix, some other set of complex numbers, and you can absorb that I, right? In other words, obviously, if this was the complex number A plus IB, and we were using this definition with, you have all your other entries here, then this ultimately is AI plus B, right? Well, if I redefine B to be A and A to be B, I get A plus IB again, right? So multiplying by a constant out in front doesn't really matter much. So Gilmore does it, so we're going to do it. So we're going to use this to represent a matrix close to the identity, understanding that the entries of M must be infinitesimal. Okay, and then maybe I'll compare it with this at the end. All right, so if I accept that this is a matrix close to the identity, let's call that matrix U, right? This is now an element, right? We're treating it as an element, an element of U2, as I said before. It's an infinitesimal element, but it's an element. And now I will now work with this formula, and I will develop some properties of M that M has to have in order for this to be true to first order. So I begin by writing down the required property in terms of this infinitesimal element near U, and I go ahead and figure it all out, right? So this conjugate transpose leaves I unchanged, gives me a minus sign on this little I there, and then it gives me M with M conjugate transpose, and then this is just I plus I M, right? So now you can tell right away, had we chosen to not use the I, then this would have been a plus, right? And we would have had two pluses on both sides, right? This wouldn't have been here. It would have been plus M conjugate transpose plus times M. And then that's got to equal I. So then we multiply these things out, and we get this, and then what happens? Well, the I squared is plus 1, but that doesn't matter because this is all going to be second order in M. So ultimately, remember, the matrix elements of M are all small. These are all small. So the matrix elements of M transpose or M conjugate transpose M or M squared or M times itself, doesn't really matter. They're all going to be small numbers squared, so they'll be really tiny and we can ignore them. So we do that. We ignore all of these. And so we draw a line. Oops. Just to keep it, I'll draw a line through it. The i's cancel. And we divide. So this becomes 0. We divide by I. And we get the final result that m minus m adjoint equals 0. Now, had we, I can't resist, had we chosen the other convention where there is no I, this would have been, this would not have been negative, so this would have been positive, not that that matters, but this would have been positive, and it would have been m plus m conjugate transpose equals 0. Okay, that's the only difference it would have made, right? Now, it seems like, well, that's a huge difference, right? Okay, well, let's kind of keep in mind that whether or not that's significant in the end, right? So we're looking for the most general matrix for which this is true. So this confused me for a while, but let me take a shot at it. So I could write it this way, right? The bar means conjugation. Right, in this case, the bar means complex conjugation. So here's a complex number z, and here's its complex conjugate, right? So what I need is m to equal m complex transpose. So you look at this and you say, okay, transposing switches z with z bar. Remember, this is a matrix with complex entries. So z and z bar switch places for the transpose. And so now I have a z up here. I might as well just do it, right? A z up here and a z bar down there. The p and q don't change places. And the transpose, so that's the transpose. Then the complex conjugation turns that back into z bar. And, well, let's see. And it undoes the z bar that I just did. So it leaves z and z bar unchanged, which is good because it's supposed to be equal. But p and q get complex conjugated. So now the diagonals won't subtract away unless p and q are real. Okay, so that's good. So that tells us what we need to know. It tells us that p and q must be real, and z and z bar have to be two numbers that are complex conjugates to each other. So I can actually rewrite this matrix as P A plus IB. Well, let's see. I'll do this. Let's do it A minus IB because I have Z down here. So Z would normally be A plus IB for an arbitrary complex number, and then Q. All right. So that matrix should satisfy this property. And if it satisfies this property, that means this is satisfied. And if this is satisfied, that means in infinitesimal form, this element of the unitary group, it means that this is satisfied, which ultimately means this is satisfied, right? So I'm looking for m's that give us infinitesimal u's that satisfy this rule infinitesimally, and that's what I just did. And this is such an m. Now, Gilmore and others will now say, well, the p and q isn't cool. Well, first of all, how many parameters are there? We can answer the question of eta right now, right? That's one. How many real parameters? Right? This is an element of our group U2, right? So there's a coordinate system, and remember, it's a manifold. It's a manifold over R eta. So I need real numbers to parameterize it. So if I'm going to parameterize it with real numbers, I have 1, 2, 3, 4. So here we have it. We figured out that eta equals 4. That's good. So we already know something about U2. I think we already knew that, but we figured it out sort of this other way. So now the other thing that's important is these guys have to be infinitesimal, right? Remember I said the only way, the way this makes sense is if M is an infinitesimally small matrix, right? Using this convention I. I guess I should look at the other way. So if this was a plus sign here, right, then we would have had M equals minus M transpose, right? And in that case, the result would have been all of this times I, right? Because we would have needed that I to fix the transpose conjugation. So what would have happened? We would have had first of all, this behaves normally, but then this I would take a -1 and turn the whole matrix into the negative of itself. So now the diagonal is purely complex numbers, purely imaginary, and the off diagonals just have to take this I. So when it's transposed, when it's conjugated, right, the transpose conjugation of these elements undoes it, but then the conjugation of this adds an additional minus sign. So the matrices would look like this if we were using the version without this I here, which, by the way, is how mathematicians do it. So this is anti-Hermitian, right? So, all right, so I guess M equals M adjoint, that is called Hermitian, right? And that's the one physicists like. Physicists like that. That's why physicists have the I here. So when we always talk about Hermitian operators in physics, it's derived from the fact, ultimately it's derived. This is where it starts, right? This is where the whole notion of Hermitian operators being such a big deal in quantum mechanics, it all begins by this convention right here, choosing to have that I pull out. That forces this matrix here to be Hermitian. Mathematicians are like, no, come on, let's speak in generalities. I plus M, right? That's all we need. We don't need your stinking convention. The problem is they end up with anti-Hermitians there, and they have their I here, right? So it's really not, it's totally a convention issue. It's completely a convention issue. All right, so let me clean this up. Okay, so I was going to say this has got to be infinitesimal. This is a general form of a Hermitian matrix, but we want it to be infinitesimal. So I've got to maybe make some symbols to show it's infinitesimal. So the way Gilmore does it is delta P, delta Q, delta A minus I, delta B, delta A plus I, delta B. He doesn't do it quite that way yet, but that's what he's implying. He throws the delta to show infinitesimals. All right, and then he says, well, we're going to count these things up. Instead of A and B, we're going to call everything theta I, right? Each of our things are going to be theta I. So the way he really wants to write it is this. So there, getting closer to his final form. Ultimately, though, what we do is instead of saying P and Q are arbitrary real numbers, we kind of put it in a slightly different form because we know how we want this to end up, and he just jumps right into it. But P and Q can always be written as A plus B and A minus B, right? For any P and any Q arbitrarily, I can find A and B such that A plus B equals P and A minus B equals Q. And that gives us our final form here, which what we really do is we adjust the parameters theta 0 and theta 3. We adjust those slightly. We choose different parameters, theta 0 plus theta 3 and delta theta 0 minus delta theta 3, right? And we haven't really changed anything except the final the form of this thing, except the structure. And so this is very close to our final form. What we do is we add an arbitrary 1/2, right? That's not going to change anything, right? Because, first of all, this is already infinitesimal. I can choose the relative values of theta 0, 3, theta 1, theta 2 freely. These are already infinitesimal. 1/2 only makes it smaller, right? So this is the form that we want to call M, right? And so any infinitesimal member of U3 is going to look like I, the identity matrix, plus I, M. That's how Gilmore wants us to do it. Now, there are other books, when you do it, it'll just be I plus M, right? And there's another way of doing it too, which is a little more complex, which is I plus sigma M, where M is a finite matrix and sigma is a, or epsilon is a small number. That's actually a little trickier because, well, we don't need to worry about that. But the point is these two conventions are definitely in the literature, and this is actually, I think ultimately this is the physics convention. This is like the pure math convention. And Gilmore rides he does a lot of math, but he's very physicsy in all of his books. He never really approaches this subject from that purely abstract perspective, which is what you would expect mathematicians to do. So when we do that purely abstract perspective, we'll see how that works. But for right now, an infinitesimal member of U3 is going to be given by this, where this is the infinitesimal matrix. And notice, everything's infinitesimal, right? And we've got this I floating out there, and there's this 1/2. So what we basically said is, therefore, this thing here describes every element of the Lie algebra. Every element of the Lie algebra, U3, looks just like that. And there are 4 parameters. We figured out there are 4 parameters for the group, but but this will be the and these are the 4 parameters, right? Sigma 1, sigma 2, sigma 3, but we got to restrict them to being infinitesimal in size. All right, so now we will break this down into delta sigma 0, right, which shows up there and there in positive form. So we write it like this, plus delta, I said sigma, but these are thetas, right? Theta 1, right, which shows up here and here, right, with an I in front of it, right? So that would be 0 minus I. No I, sorry. No I. Just, in fact, no minus either, right? Boy, I got that wrong. Like that. And then plus delta theta 2, and this one has the minus I 0. And then plus delta theta 3, which is 1, 0, 0, minus 1, like that. Right? So you can kind of see why we broke this down like this, is because we wanted these 4 things to turn out to be these Pauli matrices, right? But I have this 1/2 here that I'm dealing with, right? So I've got to put theta over 2, over 2, over 2, and over 2. And this just gets me to this expression right here, where now this is, of course, sigma 0, sigma 1, sigma 2, and sigma 3. And that was sort of the goal, is to show how M can always be expressed in this form. And then, now that we know that, we now know that any element of the algebra can be expressed in this form, so we have actually derived a basis for the Lie algebra. And that's where we started last lecture, we actually started from that basis. This is sort of showing you how we knew that that was the basis of the Lie algebra given a Lie group whose property we knew, but we don't know the parameterization of the Lie group. If we did, we would just have taken a bunch of derivatives and derived these things. But now we kind of used a different logic, created these matrices, and now we're going to work to create the actual group elements. Well, actually, I forgot. I wanted to work on SU2C, right? Right now, we've got U2C. So what about SU2C? Well, now we need to talk about the determinant of an arbitrary element U has to be 1. So let's see if we can work this out. Regular element U is going to be the identity plus IM, which will be 1, 0, 0, 1 plus, plus this guy, right, that guy times I over 2, right? You see how that I over 2 convention kind of works its way into this puzzle, this part as well, or this analysis as well. So that's what I plus IM is. So the determinant of the identity plus IM, that guy's got to equal 1 to first order. So now we're looking at this thing. Well, let's see what kind of mess we can make out of this. Let's see, I'll move it there. All right, so I think we need the determinant of this thing. All right, so now I guess I'll cross multiply this guy out. Okay, so if you multiply this times this, right, and you subtract that from that, which is the definition of the determinant, I think you get this. This here is the product of these two, and this is the product of these two. So the second part, and I'm writing squares with superscript squares. So when I write theta 1 like that, what I really mean is the theta 1 parameter squared, right? So it's not going to last long, so we don't have to worry about it too much. But the point is, the squared terms that are small, like these, we can ignore because they're second order. So we ignore this and this, which basically means we ignore all of this, we ignore all of that, and then we're left with just this stuff. But if you look, the theta 3 part, right, it's I over 2 plus theta 3, I over 2 minus theta 3. So that actually cancels out, right? So the only thing keeping this determinant from being 1 is 1 plus I over 2 theta 0, which is linear in theta, but I have 2 of those, so it's 2 of those, right? So it's, I'll just get rid of that and say it's just this, right? So this determinant to first order is not ever going to equal 1 unless theta 0 equals 0, unless this coordinate equals 0. If that equals 0, then the determinant is 1. And this makes a lot of sense, right? Because if you look at what we're doing here, is we're saying this is all the unitary matrices. They just have to preserve the metric. This guy is just that subset of these that has determinant 1. So what you're basically doing is you're taking your parameters and you choose parameter 1, you choose parameter 2, you choose parameter 3, and then you do whatever you need to do to parameter 0 in order to get the determinant to be 1, right? So you lose a dimension you lose a parameter, right? Because this parameter can be determined in terms of the other parameters. But from these infinitesimal matrices, we know what that is. And it's going to be, we want the infinitesimal theta 0 to be equal to 0. So then when we go back to this expression here, we basically lose this matrix as a basis. And so now we're dealing with a Lie algebra that is different. Now we only have a 3-dimensional a three-dimensional Lie algebra, meaning that there's three basis vectors, which means that the actual group, right, the group SU2, right, this group now, it only has eta equals 3, right? The group U2 had eta equals 4. Now we lost one by forcing that determinant to be 1. So now any element in SU2 has three basis vectors, x1, x2, and x3, and we just make our definition like we did in the previous lecture. We're going to define xi to be I over 2 sigma I, and we went through why that's a nice useful thing. That's nice and useful to keep the structure coefficients to equal minus epsilon I j k, right? It's nice to have those structure coefficients with that minus epsilon I j k, so we make this additional purely convention change, right? When we did this calculation straight up, with this basic universal matrix, where did I do that before? When we decided that this was the universal matrix for an infinitesimal transformation in this group, based on our calculation of unitarity, right? Using this unitarity principle, we came up with this matrix M that would represent infinitesimal matrices that satisfy the unitarity principle. And we worked that all out here, right? And from this, we kind of set this up with these pluses and minuses here. I kind of showed you, I showed you the logical way would be to do this. Then if we're crafty, we convert that to this. And that goal is in order to have the four Pauli matrices show up. And then when we looked at the four Pauli matrices, we now realized the any infinitesimal unitary transformation will be generated by M. So M is a member of the Lie algebra of the unitary group of 2 by 2 matrices. And then we said, but if you slap on this determinant condition, you've got to derive one of those things has to be always 0. So you lose it, and you're left with just these three. And then on top of that, when you calculate what we're not going to do, we did it last time, but we're not going to do now. If you calculate the coefficients, the structure constants, then you might choose to change your basis to this, which we do. Now you might think, well, wait a minute, these structure constants, what about the zero matrix, right? What if I or j or k is 0? Am I still closed? But you got to remember those structure constants, the first matrix, right, was the identity. And we saw this last time. It commuted with everything. So all of its structure constants were 0. So we know that all of the brackets between these three are never going to involve this anyway. Even in U3, even when it was U3, right? Well, that's what we did last time. Last time we looked at the Lie algebra of U3 because we included that first matrix. Okay, so now we're down to U2. Now we're down to SU2. So now our question is can we go from, and we already know how to go from SU2 into, I'll use the green line, to the local area around the identity. We know that is going to be I plus theta I M, well, hold on, theta I x I, right? Well, hold on, I guess I should go delta because you got to keep it infinitesimal. So I plus delta I, delta theta sub I x I. This guy here will be one of these matrices right here infinitesimally close to the identity. Now the question is can we figure out how to determine what the whole group is? Right? We want to know what is the entire, we want to map from the Lie algebra to the entire group using exponentiating any member of this, which would be, I guess we're calling it m now, right? Right? Because m is what was theta I, delta theta I. No, m was infinitesimal. M was infinitesimal, right? So let's not use m. Let's use y, where y equals any parameter value theta xi, where that no longer has to be infinitesimal. So we're looking for exp theta I finite xi. Okay, and now we'll solve this problem. All right, so this is our basis for the Lie algebra. x1, x2, and x3, right? These are our basis vectors, and we've defined them to be I over 2 times sigma 1, sigma 2, and sigma 3, which I've indicated here. You can go ahead and calculate them out too, right? If you want. This is I over 2, I over 2, I over 2, and 1/2 minus 1/2 on the minor diagonal, and I over 2 minus I over 2 on the diagonal. So those are our basis vectors. So now an arbitrary element of the Lie algebra is defined in terms of the basis, and now we're talking about the Lie algebra SU2, right? So it's a 3-dimensional Lie algebra, implying that the group SU2 is a 3-dimensional manifold, right? That's the relationship there. And it's some finite theta times these xi's, which are our favorite basis, which we chose because we like the structure constants. Ironically, we kind of immediately go back to the sigmas. It's just the way the math is done. I'm literally following Gilmore here. So this is now written like this, where I've sort of flipped. These are the matrices here, and these are the parameters, right? So these guys are the matrices, these are the parameters, so I kind of reverse the order. But remember, it's not, if these were two matrices, I'd have to be more careful, but they're not. One is a real number and the other is a matrix. Or one is these are real numbers, right? Because all the parameters are real numbers, because the parameters are the coordinates on the manifold. Okay, so with that in mind, what we are looking for is the exponentiation of, I like keeping my algebra in red for some reason. We're looking for the exponentiation of that arbitrary element of the Lie algebra. So now, so we go immediately to the definition of the exponentiation, which is the sum from n equals 0 to infinity of 1 over n factorial of I guess we'll write it as y to the n. And that obviously equals this thing. I substitute for yn, I substitute this. Notice I'm using the summation convention. Gilmore does not. He keeps the up and down indices, but he writes this as I over 2 times the sum of sigma I, theta I, from 1 to 3, right? But it's really too messy. I mean, if you got the up and down going on, the problem with it is that when you start using the summation convention, there's some tendency to think that these things are space-time related or these are tensorial quantities. And it is true we're dealing with vector spaces, so this stuff all applies, but and this is the basis, and these are the components, so I guess that all does apply. But if it all applies, then just use it. So the summation convention is in effect here, but you've got a summation here that represents the Taylor series, which defines this notion of exponentiation. And you may remember the notion of exponentiation came with doing a long infinite number of infinitesimal movements, and we ended up of infinitesimal group elements, and we ended up seeing how that just mimicked the same Taylor series that we always knew. Okay, so now we've got this guy. So what do we do with that? Okay, so the rest is actually just math, right? It's just a bunch of calculations to figure out what this thing is. Remember, it's a matrix. It's a 2x2 matrix. Just keep in mind what you're looking at. It's a 2x2 matrix, and of course this is representing matrix multiplication, and the sum is matrix addition. So all this is a matrix. We got to make a few observations. One, these are all clever observations that we learned. Basically we just have to work out. But we start by noting this guy. We want to note that the sum of 1 to 3 of our basis vector, I over 2 sigma I, if you square that, what does it get, right? We get, what we're trying to do is when we square that, I pull this out and square that, so I get the minus 1/4. And then I get this guy squared, which I've worked out here are all of these terms. Let's see, there should be 9 of these terms, right? So 3 times 3. And the matrix order is preserved, right? So sigma 1, sigma 1, sigma 1, sigma 2, sigma 3, sigma 1, all of those, the order is preserved. So let's see, how do we figure this out? We figure this out by saying, okay, well, the thetas are real numbers, so they commute, but these guys don't commute. So I can take this and this and get all right, wait, this should be easy. Oh yeah, okay, that's right. So this and this, for example, will come out and will end up looking like theta 1, theta 2, sigma 1, sigma 2, plus sigma 2, sigma 1. Now, it's a famous fact about the Pauli matrices that the anti-commutator, sigma I, sigma j, the anti-commutator equals 0 for everything in the Pauli matrices. This is the definition of the anti-commutator. It's a fact that I happen to know, but you can easily check. Just multiply the matrices out, each pair, and you'll see it's always 0. Which means this cancels, which means this cancels with this cancels with this cancels with this, and the only things that survive are the cross term, or the diagonal terms. The cross terms all cancel. But the diagonal terms, sigma I times sigma I, right? Those always equal the identity. Well, they would equal sigma 0. Sigma 0 is not really one of the Pauli matrices. It's obviously the identity. So we could call it sigma 0. So this whole expression ends up equaling minus 1/4, and it's sigma 1 squared plus sigma 2 squared plus sigma 3 squared times the identity matrix, right? So we call this just sigma squared, right? So this is now minus sigma squared over 4i, right? That's what this is. If we want to keep the squares going in the most convenient way, we'll write this the way minus 1/2 sigma squared, or 1/2 theta squared, where it's understood that that's times the identity matrix. One thing that bothers me about Gilmore's exposition is he doesn't make it clear that this thing here, when it's done, is a 2x2 matrix, right? These Pauli guys, there's nothing that can take them away from being a matrix. Unless you take the trace or the determinant of a matrix, it's always going to be a matrix, right? So I kind of want that I there. I guess the way I'll do it is not I. Let's just stick with our previous notation and go with, go with sigma 0, right? Sigma 0, to make sure that we understand this is a matrix. This is a constant, right? Because theta 1, 2, and 3, they're real numbers. So this part here is a real number, but this part here is the 2x2 identity, which we call sigma 0 for now. All right, but the reason we do that is so we can go back here and simplify this. In fact, I'll just write it on a new spot here. So we can write this down as the sum of the even powers plus the sum of the odd powers. So the sum of the even powers will be sum of, say, n equals 0 to infinity of 1 over 2n factorial times I over 2 sigma I theta I to the 2n, right? That would be the even sum. And likewise, the odd sum will be that. The odd sum will be this, but well, we add 1 down here. So when n is 0, we get our 1 over 1 term. When n equals 0, we get our 0th order term. When n equals 1, this gives us our second order term. When n equals 1, this gives us our third order term. Right? So when n equals 0, this gives you the first order term. When n equals 1, this gives you the third order term. And notice this looks like it's even, but remember, we're multiplying by another factor here. So this could be thought of as 2n plus 1, but we broke it out into these two factors in order to make things a little simpler. Okay, so then what do? Well, I squared is -1. So we have -1 to the n here is what this is. So let me go ahead and take that out, and I will put that here as -1 to the n. And likewise down here, this will be I squared. So that's again -1 to the n. And then there's another I here, but we'll leave that alone. Right? So we have so here we also have -1 to the n, but I've got to get rid of this I here. So that becomes a 1 and that becomes a 1. So I basically factored out that I. And then what have I got? Well, this thing here is 1/2 sigma sub I theta I squared raised to the nth power. But that square part I figured out over here already. I figured out with the I inside, if you square this, then you end up with this expression, right? Now, I've already accounted for that I. I've already kind of pulled that I out, so we're only concerned about this part. It's 1/2 theta squared sigma 0. So that would be this part here is 1/2 theta squared sigma 0. So I can actually erase this, and I can write 1/2 theta squared. What else? I have to erase this 2n, right? 1/2 theta squared to the nth power. Oh, wait a minute. That's not right. That's not right. Hold on. It's 1/2 theta squared to the nth power. And it's understood that this is sigma sub 0, right? Because you raise that to any power and it's still n, right? So that corresponds to this expression right here being substituted in. The 1/2 is inside the parentheses. This minus sign was accounted for when we pulled out the I, right? So this first term, the even terms, get simplified in this way. The odd terms get simplified in a similar way, and we do the exact same thing right here. Here we can't do it because we're not squaring it, right? But here we can. So I will erase this, and write it as 1/2 theta to the 2n, right? And then leave this other part. And so now what's important is to see, well, this doesn't have any n dependence at all, right? So that's just a constant as far as this summation is concerned. And these expressions we now have to study, right? So these are the even terms, and we have theta over 2, 1 over, so we only have the even terms, theta over 2, alternating in sign. Well, we should recognize that right away as the cosine series. So this first term is going to equal cosine, well, it's going to be, first of all, sigma 0, right? Sigma 0, cosine theta over 2. The second term is the odd terms, right? Because we have this 2n plus 1, and wait, they're not quite the odd terms, right? I mean, these are odd, right? But these are even. These are even. So there's a problem there. So in order to make this look like the sine series, we're going to have to multiply by, I'll do it in blue, we're going to have to multiply by another factor of theta over 2, right? We're going to have to multiply by another factor of theta over 2, which means we have to then divide by theta there. And so this guy is going to end up being plus, well, okay, so when we do that, we get the 2n plus 1 there, right? So that takes care of that. And so we get plus 2 over theta times I over 2 sigma I theta I. That's all the constants coming out. And then what's left in here, whoops, let me do that with blue. This guy here, right, now is the odd series for sine, blue, I'm still blue, sorry, is for sine theta over 2, like that. So then these 2's cancel, and we keep the I, and then we have theta I over theta. So we write that as, let's see, I will write that as plus, well, the way Gilmore does it is he writes it as I theta I unit vector, right? Because you're taking the sum over, then you have sigma I here, and then you have sine theta over 2. So this is the unit vector, sort of the unitized or normalized parameter. So the parameter theta 1, theta 2, theta 3 gets divided by this theta, which is understood as theta 1 squared plus theta 2 squared plus theta 3 squared, right? That's what theta equals. So you're kind of dividing by the magnitude of, well, that's what theta squared equals, sorry. But we're not dividing by theta squared, we only multiply by 1 power of theta. So that becomes the sort of the normalized parameter. And then you get sigma I in there, and you've got sigma 0 there. So you end up with a matrix, and that matrix is going to look like cosine. I'll do this. And here I just kind of blew it up, filling in for these theta 1s. So this diagonal element with theta 0 is cosine and the cosine. Then if you look at the theta, they keep saying sigma 1 element, but it's correlated with theta 1, or sigma 0 element. All right, so the sigma 0 element puts the cosine theta over 2 and the cosine theta over 2. So this is a number, right? Theta is a number that you calculate. Once you've chosen the parameter for the matrix you care about, you just add it up, or you add up the 3 coordinates. You add up the squares of the 3 coordinates, take the square root. You got theta divided by 2. You've got the argument. That's a number, right? So now, then let's look at sigma 1. The sigma 1 piece is going to be remember, that's been simplified to this, right? So the normalized theta 1 gets placed in the theta 1 slot, which is right here, times I sine theta over 2. Likewise here, because sigma 1 has a 1 in the lower right, the lower left, and 1 in the upper right. And then the theta 2 slot gets a minus I in the upper right, which takes care of this I. So minus I times I is positive 1. So you get that there. And then down here you just have a regular I. So I times I is minus 1. So you get this minus sign here. And that brings in that sine theta over 2. And then on the diagonal you add a plus I normalized theta 3 and minus I normalized theta 3 with sine sigma theta over 2. So all these are real numbers, or all the coefficients, well, all these are complex numbers. So you have a complex number in each slot. But of course, this is a member of SU2, right? This is the group element now in SU2. Right? This is the group element, and SU2 is, by definition, the 2x2 matrices of complex numbers. And that's what you got. So we've done this exponential, and again, it was a little bit clever, right? A little bit clever, but that's why people have done this before us. I mean, I certainly didn't invent this technique. There's another technique on how to do this, which we'll do next time when we look at SO3. Okay, so what have we done? Let me do a quick recap. We started by looking at the unitary matrix, 2x2 unitary matrices, which we understood as preserving this metric. We went back to our classical group study. We know what metric we're interested in. We're interested in the unit metric. And then that gave us the fact that every member of this group obeyed this rule, that the conjugate transpose times the matrix itself was the identity. Then what we did was we sought an element near, we looked at all of the elements of U2 that were near the identity. We knew how to write those down, the infinitesimal units. We wrote down a infinitesimal matrix in U2 that satisfied this rule, and we chose our form to be the deviation from the identity to be I times an infinitesimal matrix. That form led us ultimately to studying this infinitesimal matrix M, which we understood must be a member of the Lie algebra, because that's what Lie algebra members do, right? Lie algebra members are, when added to the identity, are infinitesimal deviations from the identity. So once we did that, we selected this form, and admittedly, this selection was a little bit leading, right? It was a little bit leading because we wanted this to end up giving us these 4 Pauli matrices. So we kind of saw that in the end. But had we not done it, eventually we would have come around to this as the most efficient way, and we've gone back and redone it. I usually don't like to do things that are leading, but I am following Gilmore, and I kind of want to explain why Gilmore got there. We did show that, this is just an alternative form of P and Q. Anyhow, but using that form, we broke it down into our Pauli matrices as our basis for the Lie algebra. And then from there, we calculated the determinant, and we eliminated one of the Pauli matrices, thereby going from U to the unitary group to the special unitary group. So we showed how that was done. And then we just exponentiated. We demonstrated the exponentiation, which used our sort of convenient matrices that are convenient basis, convenient for the structure constants, but in the end we kind of still drove the ship with the Pauli matrices. We created this object, which is the definition of the exponential, and then we just very cleverly executed that exponential using this very important identity. So using the fact that the product of any two Pauli matrices is sigma 0, and the anti-commutator of two Pauli matrices is 0, we were able to clean this up, derive this nice identity, which is a real number, right? Well, I'm sorry. Derive this nice identity, which is a multiple of the identity matrix, right? And then we drove the ship home and we calculated the actual members of U2. So these are now the functions of the coordinates, where, remember, theta is actually the sum of the squares, or the square root of the sum of the squares of the three parameters, theta 1, theta 2, theta 3, and these were normalized thetas given by theta I over theta. Okay, all right, so next time we'll do this for SO3 and draw that legendary comparison.